Saturday Morning Physics is sponsored by the Physics Department of the University of Michigan, by the Dr. M. Lois Tiffany Endowment, and by gifts from friends of the program. Local broadcast is made possible in part by Pfizer.
I started by discussing special relativity, the anti-common sense results we get for things that move very near the speed of light. These consequences included the slowing down of clocks and the contraction of lengths of objects that are moving very fast. In the second week, I showed examples of shifted colors and drastically brightened or dimmed light from astrophysical sources moving at relativistic speeds. Today I will tell you the history of a scientific mystery, how it was solved, and incidentally, how special relativity was part of that process. About once a day, there's a flash of light that passes through our solar system. For a fraction of a second to a few minutes, it can be so bright that it can drown out the rest of the sky. These amazingly intense events are easy to overlook because they don't happen in the light that we see, but rather in the most energetic light there is, gamma rays. So let's start by going over what I mean by the most energetic light. Light acts like a wave that comes in small packets called photons, shown here. Like any wave, it has peaks that come with a certain distance between them called the wavelength, and how often they arrive at us as the light travels gives us the frequency of the light. Just as you experience the frequency of a sound as a tone or pitch of a noise, the frequency of light that you see is a color, shown here with yellow. Now what happens is that when you deal with light that has a longer wavelength, shown here, the peaks come less often, it has a lower frequency, and has a lesser amount of energy per photon of light, shown here in red. If you have more cycles, the light coming with a shorter wavelength, a higher frequency, you go there to the more blue colors through violet to the higher energies. Just as you can go redder than red to lower energies like infrared and radio, you can go more blue than blue to higher energies like the ultraviolet, X-rays, and what we call gamma rays. Gamma rays are very high energy radiation. Each gamma ray photon has literally hundreds of thousands of times more energy than the energy in the photons that our eyes are able to see. This light is pretty rare on the Earth. You need a very energetic event to produce it, like a nuclear explosion. There's a lot of energy out in space, so there are gamma rays out there, although it's very difficult to detect gamma rays from space from detectors on the ground. That's because our atmosphere acts as a nice protective blanket that keeps the gamma radiation from harming us. So today I'll talk to you about a mystery in these gamma rays, a surprise discovery that occurred not very long ago in scientific terms, about a generation ago, and how scientists came to the conclusion that there was an awful lot of energy involved in the events that produce these gamma rays. This leads one to suspect there could be special relativity involved in these events because something could be moving very, very fast. So I'll review how special relativity affects the light that we see from the skies. I will talk about the hunt that went on by scientists in order to find more information about these events, specifically at longer wavelengths, more normal light, such as the light that we see. What we've been able to learn from the leftover light that comes not just at gamma rays, but at lower energies. And finish up with some of the interesting questions that we can address by studying these objects. So our story begins with a bang in the Cold War, when both sides decided that they would no longer test nuclear bombs in such places as in the atmosphere, underwater, and actually in outer space. This wasn't the sort of thing you simply signed a treaty, went away, and trusted the other side. The American military decided to verify the adherence to the Test Ban Treaty by starting a program to send up satellites. These are two of the satellites that were sent up above the atmosphere This is because, as I mentioned, the atmosphere would absorb any gamma rays from a nuclear explosion that went out in space. If you wanted to see that a nuclear explosion had happened, you'd have to start out by being up in outer space in order to notice it. So if you send something up which can just detect gamma radiation, and you see gamma radiation, you might think that a nuclear bomb had been tested there. But you have to keep in mind that outer space could also have gamma ray sources. And it would have been incredibly stupid, not to mention dangerous for the whole world, if a natural source of gamma radiation were misidentified as a nuclear test. Therefore, they brought in scientists to help them interpret what they were going to see. The scientists could use this as an opportunity to take these gamma detectors that would be in space and use it to study sources that they believed would have gamma radiation, such as flares from our own sun or supernovae, these explosions of massive stars at the ends of their lives, which are some very energetic events. So here's what happens. Gamma radiation goes through almost anything. You can't build a mirror with our present technology that will reflect gamma radiation back, focus it to a point, and allow us to make an image of the gamma ray sky. Usually, about the best you can do is just detect that gamma radiation is there, much like a Geiger counter. Therefore, what you did was you would use geometry to determine from where the gamma radiation came. So shown here are two satellites, two of these Vela satellites from the program. They're not actually attached by a rod. This just indicates that they knew exactly where each one was relative to another. They knew that distance. So if gamma radiation came off from this side, you'd see that if it came from far away, it would come on parallel lines and have a very good chance of hitting this one and this one at the same time. But if gamma radiation came from this direction, what would happen would be you'd start out here and go towards them. By the time that it reached that first satellite, it wouldn't have quite reached the second one, as you can see. A little while later, the flash of gamma light would reach the second satellite with a time delay based on this distance the light still had to travel between the two satellites. There's a very particular geometry involved here. You have these two parallel lines. You have to drop a right angle from this ray of light to this one in order to get a distance that corresponds to the time delay for the light to travel from the satellite 1 to satellite 2. If you had a pair of satellites, you might be able to determine where in the sky gamma radiation was coming from. We're going to imagine we have two satellites. The first satellite is a pink one over here. And our second satellite is a green one over here. And the satellites have, therefore, a certain distance between them. So if you had gamma radiation that was coming and it hit this one first, you would see that it would hit this one over here second with a certain time between them that would correspond to a distance traveled by light. So you take the speed of light and determine that you had a distance about that corresponded to this much. Obviously, it couldn't be coming straight down this direction, or the time delay would have been longer. So what you do is you try to find from what angle you can possibly produce the appropriate time delay. So I'm going to draw a circle here corresponding to the distance required for the time delay relative to these two satellites. So now we have a circle going around satellite number 2 that corresponds to the amount of time delay required between the two detections of the gamma radiation. And so you start looking around this circle for any direction in which you can draw a right angle and point back towards that first satellite. So if you futz around a bit, you find this one will work. This means if the gamma radiation were coming from this direction, it would have gone like so, hit this guy first, and still had that characteristic time delay distance here to get to the second satellite. The only problem is this isn't the only direction that this could work for. If you look carefully, you'll notice that you can also do it like this. there's a second direction from which the gamma radiation could have come, like this, hit the pink satellite first, and still have had this time delay to reach the second satellite, the green one. The way that you resolve this is actually by using more than 2 satellites. If we put a purple satellite up here, up in this corner, you can see that only one of 2 things can happen. Either the gamma radiation is coming from this direction, it will hit the pink satellite first, then the purple one, or the gamma radiation can be from this direction, it will hit the purple satellite first, then the pink one. So you could resolve whether it was this direction or that direction. In real life, things are slightly more complicated because it's not 2-dimensional. These 2 directions actually form, are like laying out a pair of lines that in 3 dimensions you could rotate around and make a circle on the sky. You'd have to have a cone of positions from which the gamma radiation could come from. And it just simply turns out that if you looked at the 3rd one, you wouldn't quite have resolved the issue. You would actually need a 4th satellite to pinpoint it to one point on the sky. But you could put up a lot of satellites, and this is what they did. Now you know where the gamma radiation is coming from. Fortunately, there never was the characteristic gamma radiation of a nuclear explosion coming from anywhere around the Earth. What happened instead were mysterious flashes of gamma radiation that were given the very generic name gamma ray burst, one of which I'm showing over here. It's a funny way of putting it, but before the event happened, there was nothing on the Vela satellite. It shot up very suddenly and it was very bright. From 0.1 seconds, out here is 1 second, and then it starts decaying away over a period of about 10 seconds. This was first seen in 1967, and you've got to wonder how nervous that made people. I'm trying to imagine you're a military man. Your scientists have told you that there is a flash of gamma radiation. They say it doesn't look like a nuclear explosion, but they can't explain it by all the ways they were supposed to be able to explain gamma rays. It's not the sun flaring, and there's no supernova in the position on the sky from which it came. It wasn't a mistake. It was seen by more than 1 satellite and actually seen a few times over, from different parts of the sky. However long it took them to decide this was something interesting to scientists and not to the military, it took them 6 years to unclassify it and let it be known to the scientific community. And once they did, by that time they realized that these flashes not only were mysterious, they were all very different. We have a saying in the gamma ray burst community that if you've seen one gamma ray burst, you've seen one gamma ray burst. I'm serious here. These are not from the Vela satellites. They've been taken over a longer period of time by better instruments. But what you can have happen is you can have a single, very short spike of gamma rays. You can have a series of spiky gamma rays lasting a fraction of a second. You can have periods of spiky gamma rays with no gamma rays in between that can last up to minutes. You can have single broad peaks, and you can have, well, this one's kind of hidden, but a complete dog's breakfast of gamma ray brightness occurring over seconds to a couple minutes. Well, this got scientists excited, because I think one characteristic of scientists is that the unexpected stuff you have to work hard to explain can be very fun. Moreover, the Vela satellites weren't designed to see really faint things. If a nuke is being tested in Earth orbit, it's going to be pretty obvious. So what the Velas could see were fairly bright objects. These gamma ray sources were bright with a lot of energy. So in order to study these things, the scientific community wanted something big. What they wanted was an interplanetary network of satellites that they could use to triangulate, as I was showing on the board there, or as shown in this diagram here, to find the direction to a gamma ray burst. So starting in the late 1970s, they were indeed able to develop this. An interplanetary network of gamma ray detecting satellites was managed mostly through the efforts of a scientist known as Kevin Hurley. He helped develop this fairly simple idea. You can take any spacecraft that's being sent away from the Earth and put something that will detect gamma rays, sort of like having a Geiger counter attached to a spacecraft. At various times, there have been different spacecraft involved, not just ones over in Earth's orbit, but also ones that have been sent on missions to Mars, Venus, and even to a rendezvous with an asteroid. You don't have to have the satellite or the spacecraft being designed for gamma rays. You just have to be able to hook in a gamma ray detector to it. as a secondary piece of equipment. So not only were high-energy satellites used, but also ones whose primary purpose was to look at other planets or study the sun, or even be used for meteorology studies of the Earth. It also was not just an American thing. This was an international network of satellites with American spacecraft, as well as, at different times, ones from Europe, Japan, or even at one point, India. So until 1990, so for over a decade, this was really the only game in town to detect where these gamma ray flashes were coming from. The question is, how good was it? Well, there's one big disadvantage to these, and that is that not all spacecraft are designed to be in constant communication with the Earth. It takes time to get the information from the spacecraft. At best, you could imagine minutes, but more likely it was going to take you hours or even days to get the information from all the spacecraft in the network if a gamma ray event had happened. That meant that you wouldn't be able to do a triangulation until days after the fact in many cases. Also, there's a certain amount of uncertainty in the time delays between what one spacecraft measures and another. You never measure something to absolute, complete accuracy. And when that happens, the measurement, as I was showing with the triangulation, has a little bit of uncertainty in it, which means instead of pointing at one exact point on the sky with perfect accuracy, you're pointing at a small patch of the sky. How big was that patch? Well, for the early interplanetary network, you'd be lucky to get it down to the size of the full moon. This causes us a small problem. There is an awful lot of stuff in the sky in the size of the full moon. You arrive at this information days late. The gamma radiation is long gone. You might imagine that anything energetic enough to produce gamma radiation could probably produce light at other wavelengths. So there might have been some visible light that you could have looked at when there was gamma radiation, but it's hard to imagine there would be much left days later. So you would like to see where it came from. And this is about a part in 100th of the moon across. We're looking at the Hubble Deep Field here. So we are seeing objects literally billions of times fainter than what our eye can see. There are a couple of regular stars here, and everything else, I think, is a galaxy. So imagine you have 100 times more of them than this to look through. It's difficult to say if your gamma radiation came because of one of these stars, some galaxy, or from some mysterious spot in between. In order to determine where these are really coming from, you need either a much smaller size for the position from which gamma rays came from, or you would need something very obvious in the field that was associated with the gamma rays. With very little information about what these are, that allowed theorists to go wild. Since you can't say where they're from, you don't know the distance to them. If you don't know the distance to them, you don't know how much energy is required to make these things as bright as they've been seen. Therefore, you could come up with all kinds of wild ideas for producing gamma radiation with almost no restrictions. At one point, there weren't all that many gamma ray bursts that had been detected, but there were many more theories than there were gamma ray bursts. There's a paper which I believe collated 120 or so of them. It's a fascinating subject, and it would take far too long to go through all the details. But there were many, many interesting wild ideas that turned out to be completely wrong. One of my favorites, I think, is the idea that there were antimatter comets out there that were hitting matter comets in a cloud around our solar system and producing flashes of gamma rays. So what does science do when you have this problem? A proper theory is going to make some kind of prediction. If you have an idea about how to make gamma rays, you should be able to say how much energy there will be in the gamma rays, and therefore how far away the objects would be. Or you could say how often this would happen. So you need to just get more information and test things like how often do these happen, or how bright are they, and you eliminate the theories that don't hold up. So this is how science works. Even if we don't know the exact positions, you can still get a lot more information. You can actually tell a lot about a set of objects by counting the number of objects and counting the brightnesses of them. And here are a couple of concepts to keep in mind when you're trying to figure out where things are in the sky. One is that an isotropic distribution is a distribution of sources that have the same number from every direction, the same number from over there as from over there. But this would look like on a map of the sky as shown here. We have a random distribution of points for sources. The second is whether something is homogeneous or not. Homogeneous meaning you've got the same number throughout space, the same number per unit volume. Well, that will give you a certain prediction, because if you have the same number per unit volume, the further you can probe in volume, the larger the number will be in a very particular way. Moreover, as you go further away from an object, the object gets less bright because the energy that's emitting has to be pushed into a larger area. This means that since the further away you go up in the volume that you can probe with the cube of the size, and the area that you probe, that the objects at the edge of this distribution are pushing their energy through, goes up as the size squared. As you go up in volume, you go up in number, and you go down in brightness in a very particular way. If you were to count the number that you were seeing by factors, so to speak, so you go up from a factor of 1 to 10 to 100 and so on, and see the brightness also by factors, you would see a nice straight line here for a homogeneous set of sources. So now we're going to take a look at where these things could be relative to us. This is a view of our galaxy, and you might assume that these things are somewhere around us in the galaxy. We are here. There is a plane to the Milky Way galaxy on which the stars are concentrated. So right around us, there's a concentration of stars. When you get far enough away, the stars start to taper off. There's less and less of them above and below the Milky Way galaxy. So first, think about the idea that these are relatively faint sources. So while bursts might be happening everywhere, we can only see the ones that are near us. Let's also assume that the burst sources are somehow related to how the matter is distributed in the Milky Way galaxy, and therefore with these points that represent the stars and the matter in our galaxy. So you can only see the bursts out to this far. Well, since it's concentrated along the plane here, we still have that same density of stars, and we would expect to see an isotropic distribution of sources, the same number all around us. We would also expect to see the same number density because we haven't gotten to the drop-off, top and bottom. So you'd see this distribution. Now imagine now that the sources are actually more energetic, and we are actually seeing them from further away. So while there might be bursts happening out here, we see the bursts within this volume. That means that we're starting to see the effects of the top and bottom of the galaxy's plane. We would see more sources concentrated where the stars are, on the sky map where the galaxy is, and not top and bottom. We'd also start to see that the furthest reaches, therefore the fainter objects, you're getting less of them. So you see this drop off below that line for a homogeneous set of sources. Now you can tell that in order to tell the difference between this picture and this picture, you don't need to get really accurate positions. You just need to get a lot of them in order to populate your sky map. And so in 1990, a satellite called the Compton Gamma Ray Observatory was sent up with an experiment called BATSI on it. BATSI was a set of detectors at the 8 corners of the box that forms the satellite here that were able to detect gamma rays. They were a little bit better at detecting if the gamma rays were brighter in, say, this direction than coming up in that direction. But they weren't relying on the time delays like the interplanetary network. So having all of them together in one satellite, they could very quickly get a very rough position of where the gamma rays were on the sky. Far worse than the interplanetary network positions. We're talking about 10 or 20 full moons across. But oh my, it was very sensitive, and it detected quite a lot of gamma ray bursts, about 1 a day. This is the sky map of about 3,000 gamma ray bursts. And as you can see here, they are everywhere around us with the same amount. It's a beautiful isotropic distribution. But unlike the case of what you would expect, these were coming from nearby us in the galaxy, we were not seeing the brightness distribution that you would have expected. You would have expected this line here for constant density of sources from sources nearby. There was a significant drop-off of the fainter sources. This is because the 2 examples that I showed you didn't include a third possibility. And that is that these are not just far away in the galaxy, but far, far away from us. If these sources are coming from other galaxies, well, if you get far away enough in the universe, you'll see the same number of galaxies in all directions. There's another property of the universe, and that is that if you look back far away from yourself, far away from us in the universe, you're looking back in time, because light takes time to move towards us. If you look back far enough in time, the galaxies haven't formed, stars haven't turned on, and any object which could be a source for these gamma rays don't exist yet. So you'd actually expect, if you're looking very far away in the universe, for sources to taper off. This could be the resolution of the data that we were getting from the BATSI experiment. But it has one big problem. This requires a huge amount of energy to be produced in the gamma ray bursts, potentially more than the sun produces in its entire lifetime out in the gamma rays in a fraction of a second to a few minutes. An amount of energy as big as a supernova puts out over its entire visible period, even of years. So scientists still argued about the distance. Sure, you could have it from far, far away from other galaxies, but maybe you could have a blob of sources that surrounded and englobed the Milky Way galaxy and tapered off around our galaxy, allowing us to see this drop-off in density. Nevertheless, either one of these cases requires an awful lot of energy for the gamma rays to be getting to us from either the far reaches of our galaxy or from other galaxies altogether. So this was a situation in the 1990s. And therefore, since there's a lot of energy involved, you can suspect that special relativity could be affecting the light that we see. So I'm going to review what we went over in the last couple of weeks. Special relativity is two basic things. The first is that the laws of physics are the same to you, no matter how fast you are moving. The results of your experiments will be the same. The second is the part that really turns common sense on its head. It's that the speed of light really is the same to all observers, and nothing goes faster than light. The fact that the speed of light is the same is what actually causes time to run slower for objects that you see to be moving very fast. I've discussed this using what is called a light clock, which I brought back the picture of. You have some source of light over here, which sends up a beam of light to a mirror, which reflects it back down. That distance, since you have a constant speed of light, produces a period of time, a tick period. And if you're just sitting still there, you're sending the light up, let's say it takes 1 second to come back down. If you were to see a second light clock moving past that first one here, the blue light clock, you would know that in order for the light to be reflected back by that mirror down to the blue one, it would have to take this longer path here, going up at an angle. As far as the red light clock is concerned, the blue light clock's tick path is longer. Therefore, the tick period must be longer than the tick period the red light clock is seeing for itself. But consider it from the blue's point of view. From the blue's point of view, it is sitting still, and it's the red light clock that is moving past it in the other direction. That means that as far as blue is concerned, it's just ticking the light straight up and straight down. Since the height hasn't changed from here to here versus here to here, the blue light clock also thinks it's taking 1 second for its light clock tick. Therefore, the red light clock really sees time's ticks to be longer for this moving blue light clock than the blue light clock perceives its own ticks to be. This is something which is pretty strange as far as our normal common sense is concerned. And it gets even weirder. Because time stretches, length has to contract as well when things are moving at high speeds. I showed an example where you have a cartoon of an asteroid out in the universe and two light clocks, a blue one that is attached to the point of view where the asteroid is sitting still, and the orange light clock that would be moving past it. In this picture here, the two light clocks coincide. After a short period of time, the blue light clock has sent 5 ticks up and down here, and the orange light clock has had light pass that same distance, but only goes through 4 ticks because it also has to travel along. So, and at that point, the orange light clock has passed by the asteroid. Well, from the point of view of the orange light clock, it is sitting still, and it's the asteroid that is moving past it very, very quickly. That only takes the asteroid 4 ticks. So 4 ticks at some speed for the asteroid to pass the orange light clock is a shorter distance than the 5 ticks at that same speed that, that would be the distance of the asteroid from the point of view of the blue light clock, which sees that orange light clock moving. This is a real effect in space. It's not an optical illusion. Now, adding to this, last week I talked about how when you include all of these effects of slowed down clocks, squeezed lengths, and having the same speed of light, if you have a source of light that is moving across relative to you, you would notice that if it was leaving off waves of light, they would have to, you'd have one which would start here, and that's this one over here. That's its center. As it moves off to the side, you can see that you get a distorted perspective here. From the point of view where the light source is moving towards you, those waves of light are bunching up. This is an effect on the wavelength called the blue shift. You get a higher frequency light from source that is coming to you compared to the light that the source thinks it is emitting. This means there's more energy in each photon. Now, conversely, if a source is going away from you, it can be letting off light with a particular frequency, but that wavelength gets stretched out relative to you, who's looking at it moving away from you. That makes the colors redder. It means there's less energy in each photon that you receive. Now, from special relativity, we perceive the redshift and blue shift of objects that are moving at very high speeds relative to us. In astronomy, there's another important effect that can give us a redshift. This is general relativity. General relativity goes beyond special relativity. It includes gravity and describes how the universe is evolving in time. This balloon, that I'm going to attempt to inflate without popping, we can imagine is the universe. You may be able to see that there are small stars on it. Each of these stars represents a piece of the universe, maybe a galaxy. And a long time ago, we know that the universe was smaller than it is now from various observations. So you can imagine that a long time ago, one of these pieces of the universe sent a signal of light far away to another galaxy in another part of the universe. It sent off that light with a particular wavelength, so a particular piece over here, which you repeat the wavelength on. Now imagine that since there is a long period of time that it takes for the light to get from over here to far off in the universe, we're going to see that the universe has time to increase in size. I just want that to become more obvious. During the time that the light starts out here and it's moving slowly, 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 slowly off to the other side of the universe. And let's, okay, that's enough growth for the universe for today. Okay. All right, so by this time, let's say, the light has gotten from there over to there. And you can see that space has literally stretched out. It's stretched out the sizes of things that are attached to space, like the wavelengths of light. So if the light had originally had a wavelength that you had drawn on here, it would have gotten stretched out. Now it's contracting. I'm just going to let the universe fall back to its younger state, rejuvenating it as we go. That wavelength of light, if you had drawn it out there, would have gotten stretched with the rest of space. That means that the colors of light that come from things far back in time when the universe was smaller get shifted towards the red in a recognizable fashion. And therefore, we can tell when light comes from far off galaxies from when the universe was much younger. One other thing that redshift and blue shift can do for you, other than increasing the energy for some photons moving towards you, is actually change the brightness of objects that you see in the sky. This is because your brightness is related to how much energy is being tossed at you. And as you saw with the light clock, in order for the light to catch up, so to speak, with that mirror on the light clock and get reflected back, instead of going straight up and down like it would be from the point of view where the light clock was sitting still, it had to be moving to the side. In other words, you toss light forward with a moving source. So here's a source that from its point of view is sitting still and the universe is moving past it. It is letting off the same amount of light in all directions with a particular wavelength, which I've shown here in orange. Well, when you have the point of view that this object is moving, this light source is moving, and now it's moving in this direction, it tosses most of its photons forward. Each photon that gets tossed forward gets more energy due to the blue shift of the light. So not only do you have more photons here, you also have more energy per photon. You have a big effect, a huge increase in brightness on this side, and a huge decrease in brightness from the point of view of someone who sees the object moving away. All right, enough review. Back to our regular programming. When we last left the gamma ray bursts, it was the 1990s, and the question before scientists were, are these objects from really far away at the edge of our galaxy, or very, very, very far away from other galaxies? It's kind of hard to tell this because we only had gamma rays to study. 1997, there was a revolution in our understanding of gamma ray bursts. This is because technology had improved, and there were new satellites up there that could do new things. One of them was called BepoSAX. It had an X-ray telescope on it as well as a gamma ray detector. Its gamma ray detector, without relying on the interplanetary network, was able to get rough positions on the sky of gamma ray bursts. A bit like the BATSI experiment, but with a considerably smaller uncertainty, maybe about a quarter of the full moon across. It also had the ability to determine that gamma rays had been detected, roughly where they were coming from, and repoint the X-ray telescope in about 8 hours towards that patch of the sky. Now, this is important because X-rays are a little less energetic than gamma rays, and you can just barely make an X-ray mirror. That means that you can focus X-rays down and make an image of X-ray sources, which allows you much less uncertainty in where X-rays are coming from. And when they did this, and repointed the telescope about 8 hours after a gamma ray burst event in early 1997, they saw a bright source in the field, which led them to suspect that this was something quite unusual and important, because there are actually very few X-ray sources on the sky relative to the number of, say, optical sources. With an X-ray source, which might have something to do with this gamma ray burst, you can now take a look at where that X-ray source was with this uncertainty of only 1 part in 200 of the full moon. You're also able to keep going back to that X-ray source. And now you can compare the X-ray picture taken about 8 hours after the gamma ray event with one taken days later. There was a very bright source at the center, which fades away. People were able to take a look at that X-ray position with other types of light, regular optical telescopes and even radio telescopes. And they too saw something similar. There was a source which went away. Well, if a source was there soon after a gamma ray burst and fades away, it's a bit too much to ask that this just be a coincidence. So people said this had to be associated with that gamma ray event. It helped that people have been expecting something like that. If something is able to produce gamma rays, there should be a lot of energy. Even when the gamma rays are over, there can be some energy left over, enough to power regular light for a while later. The fascinating thing that allowed people to know where these were coming from was that once the light decayed away, you could see that light source had been right on top of the galaxy. And as I told you over there, if you have light that comes from a far-off galaxy, you see characteristic shifts in the colors. It looks redder if it comes from a younger, smaller universe. And you could tell in many afterglows, this was repeated over and over, that there were actually shifts in features in the light that corresponded to the afterglows, and therefore the gamma ray bursts associated with them, coming from far off in the universe. So the answer now is gamma ray bursts do indeed come from very, very far away. And that causes a slight problem because if you look at this naively without considering special relativity, you would think there was too much energy involved. Consider the fact that gamma ray burst light curves, as I told you, were extremely variable. That means they could go up and down in brightness in periods of time of milliseconds or even less. Well, if you're going to make something increase in brightness, you can't just simply have a small patch of it increase in brightness. You really need the entire source to see a significant effect. That means the entire source has to react. And nothing can react faster than the speed of light. So during a brightening phase, you effectively have to be able to get light across a source in order to have the whole thing increase in brightness. Something that varies as quickly as the source of a gamma ray burst has to be very, very small. But then you have a lot of high energy photons in a small volume. Well, when photons with enough energy, like high energy gamma rays, get close enough, there's this lovely little equation here, E equals mc squared, which means that you can translate any type of energy into mass energy. Therefore, the photon's light energy can be used. You can have the photons go away and be replaced by the mass energy of particles. If you have a lot of gamma ray photons that are crowded together, this is actually very likely to happen because a lot of gamma ray photons will get close together and want to produce particles. That means you should have very few gamma ray photons coming from something as bright and as small as a gamma ray burst source. Obviously, this wasn't what was being seen. The characteristic of gamma ray bursts is that you get a lot of gamma rays from them. It's special relativity that comes to our rescue here in terms of understanding the sources. This problem with the size of the source and the brightness of it was called the compactness problem. This is because the source that's required to let that high energy light cannot be very dense in the light photons. If it's large enough to have the gamma ray photons spread out and not interact with each other and produce particles, but rather escape and be seen by us, it's going to be too large for that variability time scale that I told you about, milliseconds, to get the whole thing to brighten up. But to take that source that you have for gamma rays that allows the photons to escape, and imagine that the source is coming towards us very, very fast. As I reviewed, if you have a very fast-moving object, the size of the object actually contracts. You can take this source here and contract it into a smaller volume. It's a real effect on space. You can also take the light that comes out of this and boost it up in energy to the high energy gamma rays. You don't have to have quite as high energy photons here as the ones that we see. Also, we get fooled a little bit about the brightness. The amount of energy that's escaping here gets concentrated towards us and boosted because each of the photons gets a boost in energy from this fast speed. It really only looks too dense. Even though this is actually a smaller size here, this is an aspect of relativity. As I said, the result of an experiment is going to be the same from two perspectives, even if they are moving relative to each other. If light can escape from this source, even though it's been contracted from our perspective, the light can still escape and come towards us. Now, the question remains, how fast does this have to be in order for this effect to work? Well, this is all related to a stretch factor, which I've discussed over the last couple of weeks. How much you contract a source that is moving or slow down a clock that is moving is related to a factor that's called gamma. It is very strongly related to how fast the source of light is moving relative to the speed of light. If it's not moving at all relative to you, the stretch factor is 1, and you don't get any changes in your lengths and the rate at which time is flowing. To get the sort of effect to overcome the compactness problem for gamma ray bursts, we need an enormous stretch factor, more than 100, possibly more than 200 or 300. This means that the sources of gamma ray bursts have to be moving, expanding at greater than 99.99% of the speed of light. This is huge. I have talked in the past couple of weeks about things like jets that are being driven off from the centers of highly active galaxies with the energy of billions of suns. That still only produces stuff moving at about 90% of the speed of light, with a stretch factor of a few. I've talked about cosmic ray muons that are produced at the top of our atmosphere and come down towards us at nearly the speed of light, about 99% of the speed of light. That only produces a stretch factor of about 10. There is a big difference in going here from 99% of the speed of light with a stretch factor of 10 up to a stretch factor of greater than 100. These gamma ray bursts are produced by the fastest organized flows of material that we know of. So we now have evidence. We have these brightest, fastest bangs in the universe. How do we go about studying them? Well, here was our original problem. Like I said, you have very variable light curves, very variable brightnesses in the gamma rays with time from the gamma ray bursts themselves. People studied those from 1973 till the late 1990s without being able to figure out anything much about them. But take a look over on this side. You have this leftover light, this afterglow, in various wavelengths. And here are some very typical examples. Instead of fractions of a second to a minute, the scales here are actually going from maybe half a minute out to a day over here and over here. And you can see that the brightness is very gradually and smoothly decreasing over that time. These are seen not just in optical light, but in X-ray light and even radio light, this nice smooth variation here. So you have smoother variation in light with objects that can be seen for far longer than the original gamma ray bursts. So you can study them going back there repeatedly. You can see them from X-rays all the way through to the radio. So you have a very rich data set to take a look at. And they have similar general properties, which allows you to think you might be able to find things in common and get a basic picture of what's going on in every single event. Therefore, what we want to do is not study the gamma ray bursts themselves, but study this leftover light, the afterglow. So how do we go about finding afterglows? We would like to have a large set of them to study. This is the state of the art now. We no longer rely on the interplanetary network to provide gamma ray burst positions for us. When a gamma ray burst goes off, there are several satellites that are shown here that are able to detect that gamma ray bursts happen, process that information, and determine roughly on the sky where the gamma rays came from. They immediately send that information down to the ground, and a system called the Gamma Ray Coordinates Network sends easily digestible packets of information all over the place. You can actually sign up and get information on email about a gamma ray burst event. I actually have mine sent to a pager. I have literally been woken up at 3 in the morning, the fact that a gamma ray burst has happened, and telling me to go on the internet and take a look at what's going on. Are we seeing any other light, this leftover light, the afterglow? You can also send that information directly to telescopes, shown here with radio sites and optical telescopes. That would allow someone at the telescope to see that an event had happened and decide whether or not to repoint the telescope at the sky and try to look for this afterglow light. Or you can take the person entirely out of the loop, which is what we do here at Michigan. I'm with a project called ROTC, the Robotic Optical Transient Search Experiment. What we have is a small network of 4 telescopes around the globe. Our nearest one is in Texas. We also have one in Namibia in Africa, the mountains of Turkey, and out in Australia. These are connected to the internet and act robotically. They automatically, when they are given information about a gamma ray event, go and look at the point in the sky from which the gamma rays came. Because we have this global coverage, it's always nighttime at least one of these telescopes. Therefore, weather permitting, there's always at least one ROTC telescope looking at the sky at any time. That means there's a very good chance that so long as a gamma ray burst happened in the nighttime sky, ROTC can drop everything and go and look at it. These telescopes are not like the Keck telescopes and the Magellan telescopes. They aren't that impressive. They're actually about yay big. You can see for scale here our friendly neighborhood kangaroo there, or an open door over there. The point of this is that they don't see very deeply on the sky, but our job is to get onto the afterglow as quickly as possible. And keeping the telescopes small keeps them nimble and quick. This is because ever since 1997, there have been 2 things we've been trying to improve. The first is trying to get those positions of the gamma rays on the sky determined more accurately. And the second part is getting those positions determined more quickly. This is because the afterglow light is decaying when we see it. Therefore, the earlier we get on, the brighter it's going to be. If we could push all the way back to the gamma rays, we might also be able to see if there's anything funny going on with the light while the gamma rays are being emitted, and see if there's anything interesting about this transition from the gamma ray phase to this leftover afterglow phase. Well, with new satellites, this has been improving. There's a satellite called SWIFT that's been up for a little less than a year. It can determine positions down maybe a pardon 8 to maybe a pardon 200 of the full moon across for where the gamma rays are coming from. And it doesn't take 8 hours to determine that position. It takes a few seconds. Well, that's comparable to the ROTCs in terms of our response. We can drop everything and go from one part of the sky all the way over to the other part of the sky, settle down, and start taking a new picture in 6 to 8 seconds. So if you take the few seconds for Swift to recognize gamma rays are going on, the time it takes to get that information to the ground, and 6 to 8 seconds for ROTC to respond, we can respond sometimes in half a minute or less after the onset of gamma rays. There is some fraction of gamma ray bursts that is a noticeable fraction that actually lasts less than that amount of time. And we have had some success in pushing back all the way to the point where gamma rays are still being emitted. The first success with the Swift telescope was the April Fool's Day event of 2005. When I've got here, and seriously, it happened on April Fool's Day, the green points are the brightnesses that the ROTC telescope was seeing for the optical counterpart, this afterglow light, this leftover lower energy light. The red points were things taken by people later. This shows about a half a minute, a few minutes, and over here is about a day after the event. This first 5-second point corresponds to this part of the gamma ray light curve, the last peak of gamma ray emission in this roughly half-minute long gamma ray burst. And funny thing, nothing's happening here during the gamma ray event. There's no extra light associated with that big gamma ray peak. So, finishing up here, we now know of about 100 afterglows that have been well studied. What have we learned here? Well, we now have a basic picture of what's going on. There is some kind of progenitor for the gamma ray burst, which produces a lot of energy, which gets suddenly dumped into a small volume. That drives out a small amount of material very, very fast. It's 99.99% of the speed of light. It doesn't necessarily drive it out smoothly. So you can have collisions within that flow. Faster stuff hits slower stuff. That energizes the material and allows it to emit light. And that will happen in a pretty random fashion. So you get this spiky emission, which corresponds to the gamma rays themselves. After you've smoothed out the flow, and you've emitted your gamma rays, you still have energy left as it coasts out beyond the progenitor source and encounters the material surrounding it. When it encounters that material, it hits that material, sweeps up the material, gives part of its energy to that material, which helps slow it down, but also allows that matter to emit light. So it starts out with X-rays, and that peak of the emission, as it expands and slows and cools, goes down from the X-rays to the optical and the radio. And this is the afterglow light that can last for days to months. So what are we learning from studying the afterglows? Well, we have a ridiculously relativistic flow we can look at. And this afterglow light emits because of swept up material. So you can imagine that all of these things that affect that can be studied. We can see how much energy is left over after the gamma ray phase. How is the material distributed around that source that produces the gamma ray burst, because that material is what is slowing down the afterglow? How is that material swept up and accelerated and which gives it the energy to emit light? And also, the strong magnetic fields that are required to produce the type of light that we are seeing from this. This is the only place where we can study flows of materials going that fast. We cannot produce a flow of material like that in a gamma ray burst in a laboratory on the Earth. Secondly, we can try to figure out where in the world you get all that energy from. The first clue was that, as I mentioned, gamma ray bursts are found on top of galaxies. That means they're probably associated with the stars in galaxies. And stars can have extremely energetic events at the end of their lives. They can blow up in supernovas. Well, actually, in 2003, a very nearby, very bright gamma ray burst in its afterglow was seen. And that afterglow light was so bright that people were able to tell that on top of the afterglow light, there was the characteristic signature of a supernova. A supernova takes about a month to rise up in brightness, then decays away in a certain way. So able to sort out that was occurring during the early time of the afterglow. That means that at least some of these gamma ray bursts are really supernovas on steroids. They blow up a star, producing a supernova, and at the same time send off a small amount of light incredibly fast that produces the gamma ray burst. So what's left for us to study? Well, first, that might not be the only type of progenitor. There's a lot of details that go into this, but the shortest bursts, which are a little harder to study because they're harder to determine positions on, seem that they might have a different type of progenitor, a different thing that is producing that energy. We obviously don't have all the answers about these relativistic flows and how they collide with and shock material. That is because we need to sort out the many effects that I mentioned. We need to be able to confidently sort out what we're seeing in the afterglows that comes from the amount of energy or how the magnetic fields are being produced or the surrounding material. If we can do that properly, we can use gamma ray bursts and their afterglows to actually study the material around bursts in far-off galaxies. That is, when I say far off, I really do mean far off. Gamma ray bursts are so bright, they are beacons to the earliest stars, or perhaps the deaths of some of the earliest stars. They have been seen as pretty much as far away as the furthest galaxies, from light that started coming towards us literally billions of years ago. So finally, we have a basic picture, but you might still be asking, why do we still care? Apart from the fact that these are the brightest events and are associated with the spectacular deaths of the most massive stars. These are really the only way to study extremely relativistic shocks. As I told you, you cannot produce a gamma ray burst type speed for an organized flow of material in the laboratory. There's also the question of how you get all that energy out of a massive supernova explosion. Why is it happening so fast? The leading ideas are that you have a massive supernova explosion. The center of the star gets compressed and forms a black hole. Some material starts falling into that black hole and gets accelerated massively by the amount of gravity that pulls on it from the black hole. And that energy is what can be used to drive the gamma ray burst outflow. So gamma ray bursts could actually be the birth cries of black holes. And finally, I think it's good to understand these things because a gamma ray burst going off in your backyard could really ruin your whole day. It's been estimated that if a gamma ray burst occurred in our galaxy, the energy from that flash of intense high energy light hitting our atmosphere could pretty much burn up the atmosphere. That is, it could break apart all of the ozone in the ozone layer, which needless to say would not be healthy for life as we know it. I've even heard more dire predictions. If you have a sufficiently bright gamma ray burst, the light, and sufficiently nearby, the light from it could break apart the molecules in our atmosphere. It could break apart the nitrogen and break apart the oxygen molecules. These could recombine to form nitrous oxide, laughing gas. This would have used up the oxygen, so we'd be choking to death, but at least we'd die giggling. So on this Halloween weekend, I'd like to leave you with a final thought. Do watch out for those gamma rays of doom.
Saturday Morning Physics is sponsored by the Physics Department of the University of Michigan, by the Dr. M. Lois Tiffany Endowment, and by gifts from friends of the program. Local broadcast is made possible in part by Pfizer.